And continuing our discussion of comparing two different population parameters, let's now start taking a look at the idea of comparing proportions, two proportions, one from each of two groups, and then take that idea and expand it into that of an odds ratio. Let's start with the proportions, specifically the difference of two different proportions. Now, the data types applicable are nominal. If we're recording the number of women that were in favor of something, there would be yes or no, and all those yeses or nos we can calculate proportions from, but the yeses and no are in fact nominal. Okay, so let's take a look at this example. A recent survey of 273 men and 291 women resulted in 192 men and 214 women being in favor of changing the college from a semester system to a quarter system. Is there evidence to suggest more women are in favor of the change than men? Now, if this is a one proportion situation, we would say that the assumption is that p hat, the sample proportion, is distributed normal. But in this case, we have two proportions. So I need to identify this one as being for the men, and the sample proportion for the women both have to be distributed normally. And the way we would do that is with the central limit theorem. Now, if this is one proportion, we'd say n times p hat has to be at least 5, and like times n times 1 minus p hat has to be at least 5. But because we have two proportions, I need to identify this as being for the men. And then I'm going to repeat it for the women. So n sub w, p hat sub w has to be at least 5. And n sub w 1 minus p hat sub w has to be at least 5. And if you look at these proportions, you see that it is true if you do the arithmetic, because the p hat for the men was 192 over 273. And p hat women, the proportion for the women, is 214 divided by 291. So if you do the arithmetic, you see that both of these are, in fact, satisfied. So what we do now is once we show the assumptions are reasonable, we go ahead and actually complete the hypothesis test. The null hypothesis would be that pi sub w, the women, is equal to pi sub m, the men. That means there's no difference between them. The alternative hypothesis, what they're suggesting here, is that the proportion of women is in fact greater than the proportion of men. We didn't specify significance level, so just use 0.05. Now, to actually complete this, we would use a 2-prop z-test. So let's jump to the calculator, go to Stat, Tests, and you see option 6 is 2-prop z-test. Option 5 was 1-prop z-test. When we're testing one proportion against some bleed value, that's what we use. When we're comparing two proportions, we use a 2-prop z-test. Now, enter the information. What I did is I already put in here, this 214 is the number of women in favor, divided by 291. That's the number of women in the survey. X1 is the women. N1 is the total number of women, so 214 is women, yes. X2 is the number of men that said yes. N2 is the number of men in the survey. And the alternative hypothesis was greater than, so now we need to calculate. But before we calculate, I'm going to point out one quick thing. It's extremely important that in my alternative hypothesis, I had women first and then men, left to right. So what I need to do is in my calculator, I need to have the women first. This is the women's proportion, then the men's proportion. Left to right, alternative hypothesis is top to bottom in the calculator. So I'll press enter, and my p-value is 0.1981. With that p-value, that's huge compared to alpha, we would fail to reject. Now, p hat 1, this value right here, this is actually the proportion of females that were in favor, and p hat 2, that's the proportion of males. Numerically, you can see that there were, in fact, more females than males. But because of randomness, the difference between the two is not enough for us to feel comfortable, at least in terms of probabilities, that the difference that we're seeing is real. More likely, the difference we're seeing is random chance. So the p-value was 0.19, what was it, 81? Is that correct? I forgot. But yeah, 0.1981. Therefore, we would fail to reject. And the conclusion in English, don't forget, you always need to put an English statement, what your conclusion is. And in English, you simply say, there is not enough evidence to suggest there's a higher proportion of women in favor of changing the college from a semester system to a quarter system than there are men. Now, I'm going to take this idea and expand it to the idea of using an odds ratio. Now, we looked at odds in the previous chapter, and what we said was that an odds is the probability something will occur divided by the probability it will not. And the way I like to break down a 2x2 table to help me with that is for the males, I'm going to put 192 because there are 192 in favor. Then how many were not in favor? That's 81. Well, if I add those up, I will get the 273 total number of males in the study. For the females, it was 214 that were in favor, and that means 77 were not. Again, if I add those up, what I will end up with is the 291 total females in the study. Now, the odds of the men in favor, that's 192 divided by the total number of men in the study, 273. This is the probability a man said they were in favor, divided by 81 over 273. That's the probability that a man said they were not in favor. The 273s will cancel, and that will then leave me with just 192 over 81. If I divide that out, I will actually get the odds, something to 1, of a man being in favor. For the women, we have 214 divided by the 291 total number of women, divided by 77 over 291. This is the probability they were in favor divided by the probability they were not. And once again, the denominators will cancel because they're the same. And this will leave us with 214 over 77. So this is the odds of the men being in favor. This is the odds of the women being in favor. If I took it and look at the ratio of this is now the ratio of two odds. And if I do a little algebra to this, I see the odds ratio, and the statistic for that we use is lambda hat. The little hat means it's the statistic. And lambda is the only Greek symbol that we use for a statistic. All the other statistics were letters out of our alphabet. All the Greek letters were parameters. Lambda by itself, without the hat, is the parameter value. So lambda hat will be 192 over 81 times 77 over 214. So that's the probability of, the odds of males to females. And when you actually do the arithmetic on that, you're going to get 0.85, I think 3. Okay, so what this is saying, if we think of this as 0.85 to 1, for every 0.85 man that was in favor, 1 female was in favor. Well, this is suggesting that the true odds ratio, whatever it is, the true odds ratio would suggest that there's a higher odds of women being in favor than men. That's what it suggests. However, that may or may not actually be safe. We need to determine whether that's statistically significant. Now, just a couple quick things about odds. Odds cannot be 0. They have to be greater than 0, but they can go out toward infinity. They can get huge. An odds ratio of 1, remember this is a ratio. The ratio of two numbers means that they're the same. So if the odds ratio is 1, that means the odds of men would be equal to the odds of women. If we do a confidence interval, the confidence interval is bounded above 1, that means that it's not likely they're the same, that they're actually different. Therefore, if they're different, that would say it's statistically different. So, likewise, if we did a confidence interval and it was below 1, the upper and lower bounds are both smaller than 1, again, that would be statistically significant. If we look at ours here, our odds ratio is 0.853. So, roughly in here somewhere would be 0.853. If our confidence interval looks like this, in other words, 1 is not in the interval, then we say it is statistically significant that the proportion of men is fewer or smaller than the odds of women. If, on the other hand, we did it and it happened to include one that looked like this, then we would say it is not statistically significant. Now, to compute the odds ratio, we're going to jump straight to the calculator and go to Program, and go all the way down to see the program Odds CI. That's Odds Confidence Interval. Select it, run it. Now the first thing it asks for is N11. Okay, let's go back to our table here. The way we think of these tables is as a matrix. This is row 1, this is row 2, this is column 1, this is column 2. So this number that's in this cell is N11. The first one is row 1, the second one refers to row or column 1. This would then be N12, row 1, column 2. This would be N21, row 2, column 1, and N22, row 2, column 2. It's important to remember that because that's what the calculator is asking us for. So let's jump back to the calculator. So N11 was 192. N12 was 81. N21 was 214. N22 was 77. And let's have a significance level of 0.05, which means the confidence level, or level of confidence, however you want to say it, would then be 0.95. Now, there's my 0.853 I was talking about earlier. There's the odds ratio. Calculate it for you. And here is the interval. So I'm 95% certain that the true odds ratio, whatever it is between 0.59 and 1.232. So if I go back to my diagram here, 0.59 is, well, let me draw a new one real quick here. The lower bound is 0.59, and the upper bound was 1.232. So notice that 1 is in fact in the interval. So if 1 is in the interval, let me do that another color real quick. I don't like that. There you go. If 1's in the interval, this is saying it is not statistically significant. That just because the odds was less than 1, that doesn't mean that the true odds is less than 1. Now, one more quick thing here. This originally talked about women, the females. We wanted to show that the females was greater than the males. Well, there's no reason I can't take this entire row and put it up here. Just change these two. If I change these two, then this would become N11, this would become N12, this would become N21, and this would become N22. Imagine it's taken and literally making females a top row, males a bottom row. There's no reason why those rows have to be in that order. So let's go back to the calculator, and I'm going to run this program again. Only this time, N11 is going to be my females that were yes. That's 2, 1, 4. And then 77, 1, 9, 2. Then 81. And we'll stay with 95% confident. And now my odds ratio is 1.172. That means for every 1.172 female or women that were in favor, there was 1 male. But look at the confidence interval. It's 0.812 to 0.169. Once again, 1 is in the interval, so it is not statistically significant. The only difference here, this is the interpretation of women to men, whereas this was the interpretation of men to women. They mean exactly the same thing.